Okay, we are on page 34 for today, and we're going to take a look at some more scatter plots for today and these sort of curves of best fit. Okay, so for example 1 on page 34, we want to use this line of best fit that's already provided for us to answer some questions about this scatter plot. So what I'm looking at here is temperature in degrees Celsius versus sales, how much money I make in sales given the temperature. Is there a relationship here? Maybe. There seems to be, at the very least, some positive linear correlation between the temperature and sales. This is in Celsius, so I want to point out that this is somewhere around here would be like a comfortable room temperature. 30 degrees Celsius is our like 90s in Fahrenheit. So as we look at these, that's what we're looking at. Remember, 0 degrees Celsius would be freezing, okay, 32 degrees Fahrenheit, to kind of give this some context if you were unfamiliar. So the first question says, based on the model, what dollar value in sales corresponds to a temperature of 14 degrees? So I'm going to look at temperature, 14 degrees here, and I'm going to follow that to my line of best fit. Now, I don't have an actual point for 14 degrees. I've got one that's just ahead of 14 degrees, but I want to use my line of best fit, especially because it says based on the model. Based on the model means you're using that line or curve of best fit to answer the problem, to answer the question. So 14 degrees would be about here on the line. That looks like about 250 to me. Does that seem reasonable? Okay, so I'm going to say about $250. Now part B, again, it says based on the model, so we'll use that line of best fit. Predict the temperature at which you would expect to make $450 in sales. So we're flipping this a little bit. So I'm going to go to 450 and follow that to my graph. That'd be right about here. Okay. Maybe right here, somewhere in there. We'll go here because that puts us at a nice temperature. So I'm going to say about 20 degrees Celsius would be the temperature at which I would expect to make $450 in sales. So I am just looking for points on this line of best fit. That's all I've done so far. Questions for me so far? For number 2, we again have a best fit model here. This time it's more of a curve. Based on the context of our question, we're looking at the value of a car over period of time. This is an exponential decay problem. So we're going to look at how the value of the car changes as the car ages. So based on the curve of best fit, that means we're going to use the model, about how much will Judy's car be worth when it's 2 years old? So her age of car, when it's 2 years old, it will be worth about this much. So there's 8 and 12. That means this guy in the middle has to be 10,000. So maybe 10,500. It looks like it's not quite halfway. So I'm going to say approximately $10,500. Anytime we're estimating, as long as your estimate is reasonable, I'm okay if it's not exactly if it doesn't exactly match what my number is, if it's not exactly in line with my estimate. If you told me 8,000, that would definitely be wrong. If you told me 12,000, that would definitely be wrong. It's got to be above 10, but under 12. And then based on the curve of best fit, approximately when will Judy's car be worth $7,000? So this time I'm looking at that dollar amount. So there's 4, there's 8. In the middle here would be 6,000. So 7,000 would be halfway between 6 and 8. So I'm going to follow this to somewhere on the curve. That looks like about 3.5 years. So approximately when will Judy's car be worth $7,000? When it is about 3.5 years old. Questions for me so far? So if I have that model, I can use it to make some estimations, okay? No matter which variable I know, I can find the other one. On the next page, we've got information that we are going to put into a model, that we are going to create a model based on. Okay, so we're going to use our calculators for this next part. So I'm going to pull up my graphing calculator and I'm going to recreate this table in my calculator. When I do this, I'm going to use X and Y. So I'm going to let temperature be my X and the cricket chirps be my Y. So when I pull up my calculator, which I'll do here in just a second, when I pull up my calculator, I want to make a spreadsheet. I want to recreate in my calculator what I have here on my paper. So I'm going to make a spreadsheet and I want to start by naming my column headings. So this I'm going to call X, the other one I'm going to call Y. And then I'm going to type all my X values into the X column. These are all my temperatures. Don't forget to hit enter after you enter that last value. Oop, and then I'm a little too far over. I'm going to go over here to the Y and enter the matching Y into the Y column. So 57 degrees Fahrenheit, we heard 18 chirps, and then 20, and then 21, and so on and so on. I'm just copying that information from my table on my paper into my table in my calculator. And again, don't forget to hit enter after you type in that last value. And then I'm going to add a page. So Control Doc to add a page. And I'm going to add a data and statistics page. Data and statistics. I'm going to click at the bottom to assign my X variable. And then click along the left-hand side to assign my Y variable. And then my scatter plot organizes itself from there. Okay. Now what I'm looking for is a line of best fit. If I look at this, it looks pretty linear, but if I read my directions, it also asks me for the best fit line. So if I'm unsure, but I see the word line, that means you want a linear model. Okay. So from here, I'm going to hit, once I've organized my data, I'm going to hit menu. I'm going to go down to analyze, regression, and then I want it to show linear, and I'm going to use mx plus b, just like I did in the notes video. Okay. So let's click y equals mx plus b, and then I like doing this on its own page instead of a split screen. You can do the split screen with your spreadsheet, but then sometimes it makes it hard to be able to see the whole equation, especially if there's a lot of decimals. So go ahead and round this to 2 decimal places for me. You get 1.05x, I should say, minus 44.18. I'm going to go ahead and put this down for a second so I can write this down in my notes. Okay. So there's my best fit line. There's my model for this information. And then based on that best fit line, so based on this model that we've created, what would you estimate to be the number of chirps heard in 15 seconds when the temperature is 62 degrees? So what I have here is an X value. What I want to find is the Y. If it's 62 degrees, how many chirps would I expect? So I'm going to plug this value in for X in my model. And then you can type that in your calculator if you need to. We get 20.9. So we would expect about 20 chirps. We didn't quite get to that 21st chirp in time. So about 20 chirps here. B says, at what temperature would you expect to hear approximately 37 chirps in 15 seconds? This time I know the number of chirps, so I know that Y value, and I want to know what's the X that matches it. What's the temperature where this would happen? So I'm going to plug this in for Y and solve for X. I'm going to solve this for x algebraically, and then we'll talk about how you can use your calculator, a graph on your calculator to help with this. If we were not working with a linear model, this might be a little more difficult to solve algebraically. So I will look at how to use a graph for this part as well. Okay, so I'm going to go ahead and start solving for x. This would get me 37 plus 44.18 gives me 81.18 equals 1.05x. Divide both sides by 1.05. And we get x equals 71.31. Since temperature can be a decimal number, we could leave this as a decimal, 77.31. That would be okay for temperature. We didn't want to leave our chirps as a decimal because either it chirped or it didn't. So that's why I would want a whole number there. If you did choose to round this to a whole number, we'd be looking at about 77 degrees. And this is in Fahrenheit for our temperature. Now let me show you what this looks like on the calculator if I wanted to find these values using my calculator. Plugging in a value for x, not so bad. Even if you have a pretty complicated function, you can do that on your calculator page, on your scratch pad, something like that. But sometimes when I have the y and I'm solving for x, that can be a little tricky. So version A, probably not so bad. I'll show you how to do that on a graph anyway. But for part B, that's something with a more complex function that we might want to do with a graph. So I'm going to go ahead and add a graph page. And then I'm going to graph our model here. We had 1.05x minus 44.18. That was the model that we wrote down from part A. I can't see anything on here. Why not? Yeah, I need to adjust my zoom. Good. So I'm going to go to menu and then window zoom. I like Zoom Fit as a start because it scales things for me. The downside here is that I've just hopped way up. Since it's a line, I've hopped just way up to where I can see the y-intercept. I can't see the x-axis at this point. I don't need to know the x-intercept, so that's okay. But if you don't like this picture, you can then zoom out a little bit. There we go. And then maybe move this around if we want to, but that's my model, that's my linear function. Now, if I want to estimate the number of chirps that I would expect when it's 62 degrees, you can do this with a table. The only reason I wouldn't use the table here is because then you have to scroll down to when x is 62, and that would take some time. A little bit faster approach would go to menu, trace, and do a graph trace. And then type in the value of x that you want. So I want to know when x is 62, what's y? So I just type 62 on my keypad and hit enter, and it will hop there for me and give me those coordinates here. So when x is 62, my y is 20.9. I also like graph trace because you can type in any value that you want with a graph trace. So let's say I wanted 67.8. That wouldn't come up in my table unless I adjusted my settings, which again is more time, more fiddling with menus and things like that. But if I do a graph trace, I can hop right there. I can type whatever value of x I want. So plug in an x using the graph. There's an option for you. And then the other thing that we want to look at is if I know the y. So if I know the y, but I don't have maybe a nice linear function where it's easy to plug in y and solve for x, the other thing that we can do is use our graph. So I'm going to hit the tab key, and I'm just going to graph the y value that we knew. So for part B, it said, when would I hear 37 chirps? So I'm going to type 37 and hit enter to graph that. And then I'm going to look for this intersection point here. If I had a polynomial, I might have multiple intersection points, and that's okay. That would allow me to see where they all were and then find them. So then to find that intersection point, I would hit menu, go down to analyze graph, and I'm looking for the intersection of those two lines. So that would be here. We got 77.31, same thing that we got algebraically. Again, for a linear function, maybe you don't need to mess with this, but for something a little more complicated, maybe for an exponential function or a messy polynomial, this might be an easier option there. And then our last question here says, what does the model predict as the number of chirps heard at room temperature for 64 degrees? So I'm going to go ahead and do this one on my calculator. So I know the temperature is 64 degrees. So I'm going to go ahead and do a graph trace. So menu, trace, graph trace, 64. That would be right here. So it's 64 degrees, 23 chirps. Put that down and then come back over to my paper here. So according to my model, at 64 degrees, I would have 23 chirps about. Now, we actually have a recorded value for 64 degrees in our table. Okay, that would be right here. So our actual value was 21. The model value is higher than the actual value. The very last thing that we're going to cover in this unit is something called residuals. And that's the idea that we're kind of introducing here, that our model should give us a pretty good prediction, but may not be 100% accurate all the time. We're off by a little bit here. Okay, so this idea of how much am I off by? Am I always getting a model prediction that's too high? Am I always getting a model prediction that's too low? If I'm consistently too high with the model or consistently too low with the model, that might tell me that my model actually isn't very good. So that's an idea that we'll talk about a little bit later on, but an idea that's important to look at when we talk about using models to be able to make predictions on data. Okay, so that's it for our notes together for today. What I would like you guys to work on now are the practice problems on pages 36 and 37. So you've got a little bit of everything that we just did. So on page 37, you've got a table where you're going to use your calculator to create a model and then answer some questions. You've got some scatterplot correlation stuff. You've got some scatterplots with best fit curves in there, and you're going to use those models to answer some questions. So I want you guys now to work on pages 36 and 37.